So before starting the different parametric tests, we must know what are the parametric tests and what are their usage. So the tests which are used to check or test any hypothesis, whether it is going to be significant or not. And the parametric tests are the tests about which we have some assumptions regarding the form of the population. That is, basically we consider the one of the very important assumption that the parent population is normally distributed. So counterpart of the parametric tests are non-parametric tests, where we do not have consider any such type of assumptions regarding the parameters that the population should be normally distributed. So here we will be using the parametric test. It means the test about which we have the assumption that the parent population from where we are doing sampling or we are taking the sample is normally distributed. So under the parametric test, we will be discussing one sample test, t-test, and two independent sample t-test, pair t-test, and we will be discussing ANOVA as well, and definitely the repeated measure ANOVA, which is, generalization of the pair t-test. So what we do in one sample test, we check whether the sample is coming from a particular distribution. So the one sample t-test determines whether the sample mean is statistically different from the known or hypothesized population mean. That is, that hypothesized population mean coming from a particular distribution. So the one sample t-test is a parametric test, and this is also known as single sample t-test. And the variable used in this test is known as the test variable, and all the variables which are used for different test under testing of hypothesis are known as test variables. And one sample t-test, in one sample t-test, the test variable is compared against the test value, and that is coming from a particular distribution, which is a known or hypothesized value of the mean in a population. So where in that case, particularly, we will be checking whether the population is having a particular mean. Say if we are testing some, say, height of a population, then definitely we will be considering the one of the assumptions that the population is normally distributed. And if we are taking the population mean and we are estimating that, so we will take a sample from that population, and we will set a statistics x bar minus mu upon s upon square root of n, that is known as one sample t-test. And we will be this follow the t distribution, and accordingly we will be showing that whether this is going to be significant or not on the basis of the critical value, or nowadays we have p value. So on the basis of the p value, we will be deciding whether to accept the hypothesis or reject. Accept means whether the population is having that much assumed population mean or hypothesized population mean, or it is different from that one. So now there are some common assumptions regarding the parametric tests. All the parametric tests, that is all the sampling distributions which are applying, we will be applying in for testing different hypotheses, but here we are confined to t-test and f-test only. That is, we are using one sample t-test, independent sample t-test, pair t-test, and rest ANOVA, and in ANOVA we use the f-test. So these two sampling distributions are used to test the particular hypothesis. So there are some certain assumptions regarding these tests of, these are also known as tests of significances. So there are assumptions regarding test of significance, or say the sampling distributions. So what are the assumptions regarding these test of significance? So there are 2-3 common assumptions, and then some particular assumptions for particular tests. say for particular t distribution, for chi-square distribution, for f distribution, and for z distribution. So here one sample t-test is commonly used to test the following. These are the areas where this, I mean, one sample t-test is applied. So we can apply it to test statistical difference between a sample mean and a known or hypothesized value of the mean in the population. That is, we are just testing whether this, I mean, sample is well representing the population or not. So we will, on the basis of a sample information, we will be checking whether the population is having a particular mean or not. And we can test the statistical difference between the sample mean and the sample midpoint of the test variable. That is also hypothesized mean. Now the statistical difference between the sample mean of the test variable and the chance variable is that we are using that hypothesized value. And so this approach involves first calculating the chance level on the test variable. The chance level is then used as the test value, which we will be using. That is on the basis of the, say, 5% level of significance, we will be using the critical value. Again, against which the sample mean of the test variable is compared. So what we calculate the value of the statistic under investigation, and we compare it with the critical value that is obtained from the table, and by using the different level of significance. Generally we take 5% level of significance and the degree of freedom. So on the basis of the level of significance and the degree of freedom, we know the value from the table, which is known as tabulated value or say critical value, and on the basis of this we compare that calculated value which we calculate from the sample, and if the calculated value is more than the tabulated one, then we reject the null hypothesis. And what is the hypothesis here? That the particular population is having a particular mean. So if it is rejected, then that particular population is not having that mean. So there are certain assumptions regarding these are the common use, and we have some assumptions as well. So first we complete the common usage of the one sample t-test. So we can test the statistical difference between a chance score and 0, which we here take the test value. So this approach involves creating a chance score from two variables and then comparing the mean change score to 0. It means there must be what we consider in null hypothesis, that the difference between the two values or two scores is 0, and which will indicate whether any chance occurred between the two time points for the original measure or not. So if the mean chance score, change score, taking the difference between 2 points, score is not significantly different from 0. If it is not significant from 0, so no significant change occurred. So the null hypothesis will be accepted there. So there is a note for one sample t-test that the one sample t-test can only compare a single sample mean to a specified constant. That is constant mean, or sometimes we call it as hypothesized mean. So it cannot compare sample means between two or more groups. If you wish to compare the means of multiple groups to each other, you will likely want to run an independent sample t-test. So what we have in independent sample, there must be at least two samples there to compare the means of two groups, or one-way ANOVA if we are considering the analysis of comparing the several means. It means we are considering the equality of several means. So we are considering several groups, that is more than two groups there. So what are the data required? Data requirement there. Data requirement means here we will be using the assumptions for the t distribution. So first, so see, there are two, three very common assumptions for all the sampling distributions, whether it may be T distribution, it may be chi-square distribution, it may be F distribution or Z distribution. See, these tests of significances are divided in two groups. One is known as small sampling distribution, or say exact sampling distribution, and in small sampling distribution or exact sampling distribution, there are three distributions, T, F, and chi-square. And another class is large sampling distribution or approximate sampling distribution. And in approximate sampling distribution, there is one test known as Z distribution, Z square. There we calculate that is normal, but for the sampling distribution of a statistic, so there we do not call it as normal distribution, we call it as the Z distribution. So there are some common assumptions for large as well as for exact sampling distributions, and there are some specific assumptions for all different, maybe exact sampling distribution or say large sampling distribution. So what are the common assumptions? That the parent population should be normally distributed, random sample should be random, and the variable should be continuous. So these are some of the common assumptions for all the sampling distributions, and we will be studying some more specific distribution for a specific sampling distribution. So here, what are the data requirement to apply the one sample t-test? The test variable is continuous. That is, it must be measured on whether interval scale or in ratio scale. So these are two scales to measure the data in terms of quantity. That is, these are two measures which measures the quantitative data. And we know, or if you wish, then we will at last we will be discussing different measures of the data, different measurement of scales of data, interval, ratio, and nominal and ordinal for the categorical data. So later on we'll be discussing. So a score on the test variable are independent. That is, the observations are independent. That is, sample is random, and there is no relationship between scores on the test variables. Violation of this assumption will lead an inappropriate p-value. So there is no relationship between the scores. There is nothing, some auto correlation type thing is there, or say multiplicity type things is there. So random sample of data from the population, this is the same as the observations as independent. And the fourth one is that the parent population is normally distributed. That is, normal distribution approximately of the sample and population on the test variable. Now, non-normal population distributions, especially those that are thick-tailed or heavy-tailed, that is skewed distributions, so considerably reduce the power of the test. So if we are not, that is why it is very important assumption to perform the parametric test. First, we should check whether the parent population is normally distributed or not. If it is not so, then we go for the alternative of that, and that is non-parametric test. So every parametric test, we have an alternative non-parametric test. So if the population is not normally distributed, that is parent population, then we go for the non-parametric tests. So among moderate or large samples, a violation of normality may still yield accurate p-value. So what we do if there is non-normality there in the data, so what we do, we increase the sample size, and up to certain size of the population, this assumption may be ignored, as the p-value may be up to a certain level, it will be correct. So homogeneity of variance should be there. This is very important assumptions, that is variances for the population as well as for the sample, both are equal approximately, and definitely there should be no outliers. If outliers are there present in the data, then it will be going, it will be violating the normality assumption. I think it will be some skewed type of distribution. Then in such cases, we must use some robust techniques. and then we go for the non-parametric tests. Now, what is the hypothesis for testing the null hypothesis for the one sample t-test? So the null hypothesis H naught, and it is, we are considering here two-tailed. That is, the particular value is, alternative hypothesis may be of three types. This is two-tailed when mu is not equal to x bar, and one-tailed we may consider that mu is greater than x bar and mu is less than x bar. So that will be right-tailed and this will be less than left-tailed. So that are single-tailed, one-tailed hypothesis, and this is, if we are considering that mu is not equal to x bar, then it is the case of this two-tailed. So here we are considering the hypothesis two-tailed alternative hypothesis H1 of the one sample t-test, and it can be expressed as mu is equal to x, mu H naught such that mu is equal to x bar and H1 such that mu is not equal to x bar. That is, the sample mean is not equal to the proposed population mean, and this is here we consider that sample mean is equal to the population mean, where mu is a constant proposed for the population mean and x bar is the sample mean. So here what we do, we consider mu as the population mean. Now what is the test statistic? And so there is a statistic and there is a test statistic. So if we are considering the, say this is say mu minus x bar minus mu upon s x bar, that is, this is the standard error of x bar. So this is the statistic, and if mu is equal to say mu naught or it is mu, so that the statistic under the null hypothesis is known as test statistic. It means if we have formed a statistic, what is statistic? Statistic is nothing but it is the function of the sample values, and when we are incorporating the null hypothesis into the statistic, then this statistic is known as the test statistic. So the test statistic for one sample t-test is denoted by t, which is calculated using the following formula: t equal to x bar minus mu upon sx bar, where sx bar is nothing but it is s upon square root of n. That is, this is standard error of the sampling distribution of x bar. So these are the some usual notations, where mu is the proposed mean, that is population mean, and x bar is sample mean. N is sample size, then that is number of observation in the sample, and small is the sample standard deviation, and sx bar is estimated standard error of the sample mean. It is the standard error of the sample mean. The calculated t value is then compared with the critical value, which is also known as tabulated value, from the t distribution table with the degrees of freedom say n-1 and chosen confidence level, that is 5% say. So if the calculated t value is greater than critical t value, then we reject the null hypothesis, and then we will conclude that the sample mean is not equal to the population. So this is the data setup for say SPSS environment. So your data should include one continuous, one numeric represented in the column that will be used in the analysis. The variables measurement level should be defined as scale, because we are considering the continuous variable in the variable view window. We will be seeing it while practicing the things. So now, how to run one sample t-test in SPSS? So to run one sample t-test in SPSS, just click analyze, then compare means and one sample t-test, and there we will see such type of dialog box will be opened there. Here we will consider the test variable, and we'll put it here in test variable and go to the option, and if here just put the value of the population mean, that is test value, and click OK, then we will get the result, and on the basis of the p-value we will decide whether to accept the hypothesis or reject the hypothesis. So here we are looking that there are some, say, 3 points, alphabets A, B, and C. So what is test variable, what is test value, and what are the options in the SPSS. So we know test variable is the variable under consideration. Test variable, the variable whose mean.
Sorry, sir.
Pardon?
Sir, actually, we have mixed kind of participants. So they are very much confused about these terms like p-value and other things. So it would be helpful if you can interpret.
When we will be, I mean, doing analysis, say we will be discussing different interpretation, and there we will be discussing each and every value.
Yes, because they are very. It will help actually, us help him.
So definitely, I will be discussing how to test on the basis of the critical value and how p-value is alternative of that one. So while analyzing the data, so in table p-value we will be given there, and alternatively I will also discuss the critical value, how to calculate the calculated value with the tabulated value.
Okay, so participants, please have patience. So sir,
definitely you please have patience. Definitely I will be discussing what is p-value, because I know it is very important.
Yes,
to know the
because participants don't they don't have statistics background. So yes, please.
Okay, thank you. So here test variable is the variable under consideration, the variable whose mean will be compared to the hypothesized, that is population mean, that is test value. So test value is nothing but it is the population mean. So you may run multiple one sample t-test simultaneously by selecting different test variables. I mean, if you are having more than one this test variable, then you can perform many hypotheses for one sample t-test. So each variable will be compared to the same test value, but all variables will be compared with the same test value. Here we have no option to put several test values as well. So the test value is nothing but it is the population mean, that is hypothesized population mean, against which we test the sample mean. And definitely options are there given. There are so many options there in the so new dialog box will be open there, and there will be so many options. You choose appropriately, and then click continue, and then click OK. So you will get the result. So clicking options will open a window where you can specify the confidence interval percentage and how the analysis will address missing value, exclude case or include case types, and click continuous when you are finished, and then click OK. So okay. So here how to run this one sample t-test in SPSS. So you just go to analyze, then compare means, and then one sample t-test, move the variable test variable here. If you are interested in more than one test variable, then move all variable, but the restriction is that all the variable sample means will be compared with the same population mean. So okay, here we wish to check the average height is 66.5 inches, say. Then click on option and you select the appropriate things, and then click continue, and then click OK. So you will get the analysis. So you will have this type of table. This is descriptive table, and so two sections boxes appear in the output. One sample statistic and one sample test. This is one sample statistics. It means we are having some descriptive statistics here. How many cases are there? What is the mean of that sample? What is standard deviation for the mean, and what is standard error for the mean? What is standard deviation for the population, and what is the standard deviation for the sample mean. The first section, one sample statistics, provide basic information about the selected variable height, including the valid, that is non-missing sample size, mean, standard deviation, and standard error. In this example, the mean height of the sample is 68.03 inches, which is based on 408 non-missing observations. It means all non-missing observations are here 408. Now this is the main table, that is one sample test table, and you can see here A, B, C, D, E, and F. So one by one we will be discussing every one. So D is the p-value, that is significant. So what is A, the test value? We have already discussed. It is the population mean. Now B, the T, it is the T distribution, that is T statistic, which we have discussed, that x bar minus mu upon S upon square root of n. So T statistic, the test statistic of the one sample T test, denoted by T. In this example, sorry, the value of the T, this is the calculated value, that is x bar minus mu upon S upon square root of n. It means we will consider, we will calculate the mean of all the 408 persons height, and we will consider its standard deviation, and then we will put, we will calculate the T value, that is x bar, that is sample mean, and minus mu, population mean. We have set it as 66.5. So x bar, that is sample mean, minus, and sample mean is this one. So we will get the difference and divide by the standard deviation upon square root of n, and the number of cases are 408. So this way we will calculate the value, this T value, and it comes out to be 5.81. Okay, this is the degree of freedom, that is n minus 1, since we are considering 408 cases, and so minus 1, that is 407. This is the actually P value. P value is nothing but it is the probability value that the null hypothesis is true when it is actually true. And sometimes P value is also known as the actual level of significance, because sometimes we go through different examples where the null hypothesis is accepted for 5%, say 1% level of significance, but it is rejected for 5% level of significance. So since the level of significance are predetermined, so sometimes if the critical value is lying in between 5% and 1%, so it is very hard to decide whether to take 1% level of significance or 5%, because at 1% significance it is lying on the region of acceptance, so the null hypothesis will not be rejected, and for 5% level of significance it is lying in the critical region, so we are rejecting the null hypothesis. So there must be some measure which actually measures, which actually decides the boundary, the critical value, the critical region on the basis of the data in hand. So that measure is the P value. And on the basis of the sample data, the critical value is fixed, and we calculate the P value for different samples possible, all possible samples of the statistic under consideration. So it is the probability that the null hypothesis is true when it is actually true. So if P value is higher and higher, it means the probability that the null hypothesis is true when it is actually true. If it is very high, it means we are close to the null hypothesis. So their null hypothesis will not be rejected. And if the P value is less than 0.05, it means we have very low probability that the null hypothesis is true when actually H naught is true. So very low probability, it means we will the null hypothesis is not true. So there we reject the null hypothesis on the basis of the P value. So if P value is less than 0.05, we reject the null hypothesis. If it is more than 0.05, we do not reject it. So here all are the values which we have discussed. This is the P value corresponding to the statistics. and mean difference, it is calculated on the basis of these differences, we calculate the critical difference. And with the value of the t value from the table, we calculate the critical difference. If we are having critical difference, so when the null hypothesis is rejected, then we see which pair of treatment is significant, responsible for this rejection, but that is for the 2 sample t-test, not for this one. Here the difference between the sample mean and population mean, if it is significant, then we decide that sample mean is not equal to the same population mean, and we reject the null hypothesis that the particular population is not having a particular population mean. And we can calculate this confidence interval for this difference as well. So the confidence interval for the difference between the specified test value and the sample mean, so that we see what is the length of the confidence interval where the value of a statistic is lying for different, for rather say for all possible sample, all possible samples under consideration. So definitely we know the decision is taken on the basis of the p-value. If it is less than 0.05 at 5% level of significance, if p-value is less than 0.05, we reject the null hypothesis. If we are taking 1%, then if it is less than 0.01, then we reject the null hypothesis at 1% level of significance. Okay, now we come to independent sample t-test. So here we are moving one step ahead. There we have tested only one sample t-test. Now we are testing the independent sample t-test. It means we are testing the equality of means of 2 populations, 2 independent populations. So the independent sample t-test compares the means of 2 independent groups in order to determine whether there is statistical evidence that the associated population means are significantly different, or we check whether the 2 populations, 2 samples are coming from the same population. So the independent sample t-test is a parametric test, and this test is also known as independent t-test, independent measure t-test, independent 2 sample t-test, student t-test, 2 sample t-test, uncorrelated score t-test, unpaired t-test, unrelated t-test. So there are so many names of this independent sample t-test. Now the variables used in the test are known as, we know, dependent variable is the test variable and independent variable are the grouping variable. So grouping variable is a categorical variable. See, we have maybe a slide maybe at last, but if we are dealing with the dependent and independent variable, then there are 4 possibilities of the natures of the variables. That the dependent variable may be numerical and non-numerical. It means it may be qualitative, quantitative, or say scale and categorical, and independent as well. So there are 4 combinations, then both variables are continuous, then one is continuous, another one is categorical, then another one is continuous, and first one is categorical, and both are categorical. So in 4 situations, we use different statistical tools to analyze the data under consideration. So here ANOVA is applied, or say this is these tests are applied where we use the, for especially for this analysis SPSS, we use one that is test variable, which is numerical or continuous, and another one is grouping variable, and that is categorical or say non-metric. So there are common uses of independent sample t-test. So what are the common uses? That is statistical difference between the means of 2 groups. If we are interested in testing the equality of 2 means of 2 groups, equality of means of 2 groups, statistical difference between the means of 2 interventions. If we are some say we are intervening some drugs, or say some vaccines to do 2 different groups, and we are interested in testing the equality of the average impact of the two interventions. So, and the third one is statistical difference between the means of two change scores. We see where there are differences in changes of two scores from 0. So now there is a note for this test that the independent sample t-test can only compare the equality of two means only. And if we are interested in comparing more than two means, then we will go for the ANOVA, that is analysis of variance. Same data requirement is, required here, that the dependent variable must be continuous. Independent variables are categorical. Cases that have values on both the dependent and independent variable we will consider. And independent sample tests are groups. Independent sample observations, it means the observations in each independent sample are independent. There is no relationship between the subject in each sample. It means the observations are not associated to each other. This means that subjects in the first group can also be in the second group. Cannot be, there should not be common in between two groups. So no subject in either group can influence subject in the another group. No group can influence the other group. And violation of this assumption will lead an inaccurate p-value as we know. Random sample from the data from the population. We have, this is also the assumption that the observation should be independent. This is the same assumption. And normality assumption should be there. So before performing any parametric test, we have to first test whether the population is normally distributed or not. Parent population from where we have done something. So non-parametric non-normal population distributions, especially those that are thick-tailed or heavy-tailed, as we have discussed earlier, considerably reduce the power of the test. So in such cases, we go for the non-parametric test. So among moderate or large samples, a violation of normality may still yield accurate p-value. We have already discussed the same assumption that to violate or to hold p-value accurately, what we will do, we will increase the sample size when non-normality is there in the data. So homogeneity of variance should be there, that it variances are for both the populations should be, both the samples should be same. When this assumption is violated and the sample sizes for each group differ, the p-value is not trustworthy. So there is a test for this test, equality of variance also. So there we check first the equality of variance, and accordingly, if both the populations are having same population variance, then we use the t statistic, simply use, that is x1 bar minus x2 bar upon s square root of 1 upon n1 plus 1 upon n2, where s is the combined variance, combined standard deviation for both the samples. And if it is not met, this assumption that the population variance of both the population are same, then the degree of freedom is adjusted for that one, and then we use the t value, but for the with the degree of freedom adjusted. And we know that there should not be outliers in the data. Otherwise, we will go for the some robust measures. Note, when one or more of the assumptions for the independent sample t-test are not met, you may want to run the non-parametric test. And the non-parametric test, which is equivalent to independent sample t-test, is the Mann-Whitney U-test. So Mann-Whitney U-test is applied there when the assumption of normality basically is not met for the parametric distribution for testing the independent sample t-test for two samples. So researchers often follow several thumb rules. What are the thumb rules? each group should have at least 6 subjects. We know if the observations are 6 or lesser, then it is better to use non-parametric test than the parametric test. So it means if you wish to perform the parametric test, then the observation must be greater than 6. And inferences for the population will be more tedious with too few subjects, and it will also be, I mean, a problem to get the inferences for the population on the basis of the sample having very lesser observation. Now a balanced design, that is same number of subjects in each group, that is balanced design is it means if we are comparing the equality of means of two groups, then the number of observations in each group should be same. And if you are dealing even for more than 2, then the number of observation in each group must be same. So extremely unbalanced design increase the possibility that violating any of the requirement or assumptions will threaten the validity of the independent sample test. It means even if we are dealing with the unbalanced data, unbalanced groups, so there should not be a huge difference between the number of observations of one group and the number of observations of the another group. So these are the hypotheses for the independent sample t-test. What are the hypotheses? That is, the null hypothesis that the mean of the population mean of the two populations are same, and the alternative hypothesis is that it is not same. And similarly, you can see the difference is 0 and difference is not 0. And we know that mu1 and mu2 are the population mean for group 1 and group 2 respectively. Notice that the second set of hypothesis, this one, can be derived from the first set by simply putting it this left side, and you will get the. Now we will see Levin's test for equality of variance. So first if you are performing independent sample t-test, first you check the normality of the data, then you go for the equality of variance of the two groups, and Levin test is there to test the equality of two variances. If the equality of two variances are not same, then I have already discussed that we use the value of t, that is calculated value of t, but with the adjusted degrees of freedom. Okay, so recall that independent sample t-test requires the assumption of homogeneity of variance, that is both group have the same variance, and SPSS conveniently includes a test for the homogeneity of variance called the Levin's test. Whether you run an independent sample t-test, and automatically it will be shown there, and on the basis of the p-value for the Levin test, we use the appropriate test value. The hypothesis for the Levin's test is that the variances for both the population are same, and the alternative is that the variances of both the groups are not same. So this implies that if we reject the null hypothesis of Levin's test, it suggests that the variances of the two groups are not equal. That is, that the homogeneity of the variance assumption is violated. And if it is so, then we adjust the degree of freedom, and accordingly for the adjusted degree of freedom we can see the p-value. See here. Okay, this is the test statistic for testing the equality of two means by considering the assumption that the population variances of the two groups are same. The meaning of all the symbols are same as we have discussed earlier. That is x1 bar, it is a sample mean for the first population. This is the sample mean for the second group, or say second population. N1 sample size for the first group sample, N2 is the sample size for the second sample. S1 is standard deviation for the first sample, S2 is standard deviation for the second sample, and SP is the combined standard deviation, or say combined, or say pooled with standard deviation, and the formula is here. Okay, so what we do, we just see whether the Levens test is significant or not. If it is non-significant, then we simply calculate the value of T at N1 plus N2 minus 2 degree of freedom. And if Levens test is significant, then we adjust the null hypothesis. Sorry, we adjust the degrees of freedom with this formula. So with this formula, the degree of freedom is calculated, and on the basis of the degree of freedom, we calculate the tabulated value of T distribution with this degree of freedom and 5% say level of significance. And then we calculate, we compare it with the critical value, and if it is greater than that critical value, then we reject the null hypothesis. Otherwise, we have no evidence to reject the null hypothesis. Note that this form of the independent sample t-test T statistic does not assume equal variances. This is why both the denominator of the test statistic and the degrees of freedom for the critical value of T are different than the equal variance form of the test statistic. So it is different from the T value for the equal variance assumption. So data setup, we know all the same things should be there. Your data should include two variables, as we have discussed that one is the test variable and another one is the grouping variable, that is categorical variable, and then we calculate the T value. So how we will run it in SPSS? So we will click on analyze, then compare means, and go to independent sample t-test. When you will click independent sample t-test, then this type of dialog box will be opened there, and you can see here, just you have to put the test variable here. One more thing, while you are performing the independent sample t-test, so we set the all observation of one group in a column, and all the values of the second group in the same column, but at the second column we assign the codes to different two groups. Suppose we have just given code 1 to first group so far, in front of all the observations of the first group, we will put the value of the code as 1 1 1 1 1 1 and so on. Then 2 2 2 2 2 for the second group observation. So now that is the code, or say grouping variable, and that will be put here, and the test value variable will be put here, and then we will go for the option and then click on continue, then click OK, and then we will get the analysis this way. We have to define group actually. So 1 for one group and 2 for two group. And if we are having a say large data and we have no two groups, but we are dividing the data into groups, so you will have to define a point from where say if we are using the vaccination, say for more than 40-year person and less than 40-year person, so the cut point will be 40. Through this box plot, we generally check whether the data is normal or not. Okay. Now, if you are performing the independent sample t-test, this group statistic will be open there. That is non-athlete and athletes. We have taken two groups, and 2 to 6 persons are there in one group, and 166 in the another group. That is non-athlete group and athlete. So these are the mean for the two group variables. These are the standard deviation, and these are the standard error for the mean under consideration. and we can perform the Leven's test. Okay, so this type of dialog box, or say output, not dialog box, this is the output. So this type of output will be displayed there in the SPSS output. And what we do, we'll see, first we'll see the Leven's test. So we will see the p-value for the Leven's test. If it is less than 0.05, it means the null hypothesis for Leven's test is rejected, and the null hypothesis for the Leven's test is that the variances of both the population are equal. And here we can see the p-value is less than 0.05. So the null hypothesis is rejected, that the equality of variances of the two populations are there. So since equality of variance is not met, so in that case we will use this line, equal variance not assumed. And you can see here the degree of freedom is adjusted here, and through that formula it comes out to be 315.846, while the value degree of freedom was 390 for equal variance. And on the basis of the p-value, this p-value, we will decide whether to reject the null hypothesis or accept the null hypothesis. So on the basis of this p-value, since it is very much less than 0.05, so we reject the null hypothesis that the means of the two groups, are say two populations, are same. Now we come to paired sample t-test. Okay. So there is situation where we get the sample observation, or say observation on the same sample twice. Suppose we wish to test the glucose level in the body, blood glucose. So we take the sample at fasting and then CPP. So we check the glucose level through the meal. And now alternatively, if we wish to check whether the insulin is, effective in reducing the blood glucose or not, then before insulin, we will have the data of glucose in the blood, and after insulin, we will check the data, the values of the blood glucose, and we will take the difference between the two and we'll set it to 0 for the population, and we'll check whether it is going to be significant or not. If it is significant, it means the drug is effective, or say insulin is effective, and if it is the null hypothesis is accepted, it means there is no impact of insulin on reducing the blood glucose. So this test is also known as dependent t-test, paired t-test, or repeated measure t-test. And the variable used in this test is known as dependent variable or test variable, that is continuous, measured at two different times or for two related conditions, or say units. These are some common usage of paired t-test. Statistical difference between two time points, statistical difference between two conditions, statistical difference between two measurements, and statistical difference between two matched pairs. So this way we can perform there are so many other areas as well where we can apply this paired t-test. So note that here paired t-test, sample t-test can only compare the means of one and only two related pair units on a continuous outcome variable that is normally distributed. The paired sample t-test is not appropriate for analysis involving the following, that is unpaired data. There we use independent sample t-test. Comparison between more than two units, that is more than two groups. So there we will be using repeated measure ANOVA. And a continuous outcome that is not normally distributed, then we go for the non-parametric test. And ordinal or ranked outcomes, so ordinal and ranked data is there, then we go for the non-parametric test. Now to compare unpaired means between two groups on a continuous outcome, that is normally distributed, choose the independent sample t-test, obviously. And to compare unpaired means between more than two groups on the continuous outcome that is normally distributed, then we go for the ANOVA. And if we are doing comparison between say two groups but having non-normal data, then we go for the equivalent non-parametric test, and that non-parametric test which is equivalent to paired t-test is the Wilcoxon signed rank test. So there we will use that one. So if we are using say categorical data, then we go for the non-parametric test, and the equivalent non-parametric test for the paired t-test is the Wilcoxon signed rank test. Now these are the data requirements which are common for all the variables, all the tests which we have discussed. So I am just skipping it. Now these are the hypotheses. We know the population mean for both the observations. Yeah, both the population are same, and it is not same for the alternative hypothesis. Now this is the test statistic, that is we consider the score difference between the two population is 0, and here it is the sample difference of, this is the mean of the difference of the two samples. Here we are not taking two samples, actually here we are taking the observation twice, before and after. Anyone is having any problem? Please don't draw anything on the screen. And if you have any query, any question, please note it down, and we will be discussing at the end of the session. So, and this is the organizers are please requested to, off this for the participants, this option. So here, this is the standard error of the sample mean for the paired observation, and we know rest of the things are same as we have discussed. This is the sample mean for the differences of the two groups, and these are the, this is the sample size, and this is the standard deviation of the differences, and this is the standard error for the mean of the difference of the observations. And we know that although it is a old technique that this calculated value is compared with the tabulated value taken from the table with the appropriate degree of freedom and appropriate table of significance. But nowadays in all softwares, p-value is given as an alternative to the critical value. So on the basis of the p-value, we decide whether to reject or not reject the null hypothesis. Data setup, we know that we are considering the continuous variable, and another one is categorical. So here we don't need of that categorical variable. We take the observation twice, and we take the difference, and then we apply the test statistic. So to apply this, paired sample t-test in SPSS, we click analyze, then compare mean, then paired t-test. So this dialog box will be opened. It's such type you will perform analyze, then compare mean, and then paired sample t-test. So this dialog box will be opened. You put one variable in variable 1, and another one is in variable 2, and go to the option. Otherwise, you just click on OK. So you will get this output. So here we can see here, if here we have taken 398 persons for the test of two subjects, English and mathematics. So you can here see here that the mean score for the English is 82.7, and for mathematics it is 65.4. And these are the standard deviations, and these are the standard error for the mean. Now this is the table for the paired t-test, and you can see here the p-value is less than 0.05. So it means that the mean score for the English and mathematics are significantly different for the same class. As you can see here, if you are looking for the correlation in two subjects, so they are very weakly correlated to each other, mathematics and English. Only 24% similarity is there. Now we know that decision is taken on the basis of p-value. So here we can see here the p-value is this one, and on the basis of the p-value, we here we reject the null hypothesis since the p-value is less than 0.05. So obviously we will reject the null hypothesis. Now very quickly we move to one-way ANOVA, which is nothing but it is an extension of the independent sample t-test. So here what we check, we test the equality of several means or equality of more than two means. So this ANOVA is also known as one-factor ANOVA, one-way analysis of variance. ANOVA is taken, it is the short form of analysis of variance. AN for analysis, O for off, and VA for variance. So ANOVA is, it means analysis of variance. And it is also known as between subject ANOVA. So the variables we know, the one is continuous variable, that is dependent variable, and independent variables are the grouping variables, and these are the categorical variables. This variable divides cases into two or more mutually exclusive groups, that is grouping groups. These are some common uses of the ANOVA, one-way ANOVA, that is field experiments. In field studies we use one-way ANOVA, in laboratory experiments we use one-way ANOVA, in post experiments we use one-way ANOVA, and so many fields are there we apply this ANOVA. So one-way ANOVA is commonly used to test the following, that is statistical difference among the means of two or more groups, statistical difference among the means of two or more interventions, and statistical difference among the means of two or more change scores. Here we can see we can also perform this ANOVA for the two group testing as well, because independent sample t-test is a particular case of ANOVA. So if you we will use only two groups, then this ANOVA will reduce to independent sample t-test. So we can use it for the two independent sample t-test as well, independent samples. Note both the one-way ANOVA and the independent sample t-test can compare the means for two groups. However, only the one-way ANOVA can compare the mean scores more than two groups. If the grouping variable has only two groups, then the results of a one-way ANOVA and the independent sample t-test will be equivalent, as we have discussed earlier. And in fact, if you run both the independent sample t-test and one-way ANOVA for the two groups, in this situation, you should be able to confirm that t square is equal to f. It means there is a relationship between t distribution and the f distribution, and we know it is theoretically well established that the square of the t distribution follow the f distribution. Data requirement is common with the previous test, and homogeneity of variance should be there. Sphericity variable, we use the option there. And the null hypothesis for the one-way ANOVA is that the mean scores for all the groups are equal, and the alternative is that at least one is different from another one. So here we use two-tailed test. So this type of ANOVA is performed there. We calculate different. I am not going into the detail of the theoretical part of the analysis of variance, where the total variance, total variation in the data is partitioned in different groups. Basically, in two groups, one variation coming from the natural source of variation, that is random causes, and the another coming from the assignable causes of variation. And we have no control on the random causes of variation. Generally, the natural disasters comes into this category, and the assignable causes of variations are caused by, say, human error, and we have a control on them. We can detect them, we can identify them, and we can eliminate them as well. So if now the assignable causes of variation, if there are only one source cause for the assignable causes of variation, then this is one-way ANOVA. And if there are two sources of variation for the assignable causes of variation, then this is the case of two-way ANOVA, and so on. So this here you can see here different sum of squares are calculated. The total sum of square is partitioned in different sum of squares, and their corresponding degrees of freedom are calculated. And when the sum of squares are divided by the respective degree of freedom, then it is changed into the mean sum of square. And the ratio, these are the variances, and the ratio of the two variances follow the F distribution. So this is the variance ratio, and it follow the F distribution. And then this is the calculated value, and on the basis of the tabulated value, we see whether to reject or accept the null hypothesis. Or nowadays we calculate the p-value, and the basis of the p-value, if it is less than 0.05, we reject the null hypothesis, and if it is more than 0.05, we have no evidence to reject it. This F. Okay, so how to perform this one-way ANOVA? In SPSS, go to analyze, then compare means, and go to one-way ANOVA. And you will see this dialog box will be open. You have to just put here the test variable, and here factor, that is grouping variable actually. And you have to define different groups. You can go for the contrast, and you can see the option, and you go for the postdoc test. It is also known as multiple comparison test. It is applied when the null hypothesis is rejected. It means the means of several groups are not same. Then we go for the test, which pair of treatment is responsible for this rejection, or say responsible for the significance. So we check, and every treatment mean is compared with all the treatment means. It means every group is checked, compared with all different groups, and we see which is going to be significant or not. So, okay, this is the postdoc test, or say multiple comparison test, and there are so many multiple comparison tests. Then we generally select this Tucky test. Some of the statisticians check this Bonfermi test, and some Duncan test. So generally, I used to use this one, Tucky test, and the level of significance is 5%. If you wish to change it, then you can put it as 1%, and otherwise by default it is 5%. And click on continue, and then click on OK. Then this output dialog will be opened there, and you can also plot this graph of that one. So from this table of ANOVA, one-way ANOVA, you can see the p-value is very much less than 0.05. So on the basis of p-value, we conclude that the equality of three means of the three groups are not same. Now we come to repeated measure ANOVA, which is an extension of the pair t-test. Here we check the equality of means of more than 2 repeated observations. So to perform this repeated measure ANOVA, we in SPSS, what we do, we click on analyze, then we click on GLM, that is general linear model, and there we select the repeated measures, and then this way suppose here we have these repeated observations, and then you click that one. So you have to select here, decide here how many factors are there. It means how many groups we are considering, how many repeated observations we are using. So here we are using 3, and you just number them, 3 levels. You can name here, and then define group, and then continue. So this way, all the variables will be there, all the observations will be here. You either you put one by one or select all and click on this arrow. You will find all the variables here. And now you can go for the plots, postdoc test, contrast, and you can check the model as well. And you go for the option to save certain observations. You click on option, so you can go for the descriptive statistic estimates of effect size, and you can check for the homogeneity test. We must check it, and you can have some another, and you can go for the residual plot, and you can go for the general estimation function as well. So this way you have so many observations there. You can use the transformation matrix and then click on continuous, and then you will get this way, this type of analysis. This is the descriptive statistics, and then this is much less test for the sparsity, that is it tests the equality of several variances of different groups. As we have applied Leven's test for the equality of two variances, equality of variances of two groups. Here we are checking the equality of variances of several groups. So we will perform this much least test, and on the basis of the p-value given here, we can say that the variances of all the groups under consideration are same, because p-value is more than 0.05. So this way you can see here, and by applying this within subject effect, you can see which is going to be significant or not. So here you can see here all are going to be significant with ANOVA. So this way, and you can hear pairwise since it is rejected. So now we have performed the postdoc test, and on the basis of the postdoc test, we can see the first group is compared with the second one, third one, then second one is compared with the first one, third one, then third one is compared with the first one and second one. So on the basis of the p-value, you can see here first and second is going to be non-significant, as it is first and second are not significant. They are not having so much difference in the means, because p-value is more than 0.05. But first and third is having significant difference, and we can check it through the mean observation in descriptive statistics. You can see here first and second are having 2.8 and 2.4, while third one is having 1.9. So 2.8 is different, very much different from 1.9. So this way we can check, directly see that first is going to be significant with the third one. This way. And first and third is significant, but second and first is non-significant. Second and third is non-significant, because you see here there is not so much difference in 1.9 and 2.3. So this is also not significant. So this was all about the parametric tests. Now, so here we have a case study. ABC company launches a new brand of AC air conditioner for its customers and claims that under normal circumstances, the average life of air conditioner is 5,000 days. A retailer wants to test these claims and has taken a random sample of 10 air conditioners. Retailer tests the life of the AC under normal circumstances, and these are the number of days of their, say, survival of performance, their life. 1, 2, 3, 10 ACs, and these are the number of days of their performance. Okay. So now let me see this one. So now to perform this, ANOVA, that is one sample t-test in SPSS, we will go to analyze, then compare means, and then we'll go for the one sample t-test. Now you have to put the days, because it is the test variable, and we'll put into test variable. Now what is the value? That is population mean, and we have test set it at 5,000 days. Now we'll go for the option, 95% confidence. Oh, no problem, no issue, and you just click on OK. So you can see here, this is the descriptive statistics that we have 10 observations, and the average of all 10 observations, that is 10 AC, is 4,880 days. And this is the standard deviation, and this is standard error for their means for the samples. And this is the t-test, one sample t-test. You can see here, this is the calculated value, that is x bar minus mu upon s upon square root of n, and mu is 5,000 days. So here you can see, and the mean for the 10 samples is this one, x bar minus that, and standard deviation is this. So you can, standard error is this. So you can apply, I mean, you can calculate this value from these observations. And so degree of freedom is 9, and say we are taking a level of significance at 5%. So we will see that value of t from the table, that is tabulated value or say critical value at 5% level of significance with 9 degree of freedom, and it will be compared with this object value. If that is, I mean, this one is greater than that one, so the null hypothesis will be rejected. And here we consider actually modulated t value. So here 1.07. I mean, if the calculated value is greater, this one is greater than that tabulated one, we reject the null hypothesis. And now nowadays here we see we decide on the basis of the p value, and the p value for two-tailed alternative is that 0.311, which is very much more than or greater than 0.05. So here we do not reject the null hypothesis that the per average life of say AC is 5,000 days. So here we accept the null hypothesis that the average life of AC is 5,000 days. Okay. So let me cut it. Now we come to independent sample t-test. So first we see the case study. So the case study is that the example to know whether the salary of male faculty members in private institutions is equal to the salary of female faculty members. Researcher collected data from 20 male and 20 female faculty members. These numbers may differ. And that will be the case of unbalanced groups in private institutions to know the difference. So let me open the data in SPSS. Okay, so you can see here this data is opened here in. Okay, so here you can see here we have just coded this one as gender. We have given the code as this is the grouping variable, and these are the salaries of different person. So here from this, here you can change it as that one is coded for male and 2 is for the female. And now to perform the, I mean, if you wish to check the normality, then you should go for the you will have to cut the data for 1 and 2, or we can see whether it is doing for all the 2 codes. So you just click on analyze and go on descriptive statistics, and then click on the descriptive statistics. So here you just click on this one and go for the option. So okay, no normality test is there. Okay, so let me finish it. You click on descriptive and go for the frequencies. Okay, so you click here and you go for the statistics. There you can have a Normality test must be there. Okay, no. Okay, chart is there. So you can go for the explorer, for the dependent variable, you go for the statistic, you go for the plots, and you go for the normality test. Okay, so you have to perform, I mean, this you have to go to say analyze, then descriptive statistics, and in descriptive statistics you just go to explore, and there you just put it in dependent variable and go for the plots directly, and you can go for the say histogram, and if you don't wish that one as well, then go for the normality plots with test. So you click on OK and click on OK. So you'll see the normality plot with test. So this is the normality test, and two tests for the normality are applied there. One is Kolmogorov-Smulders test, and the another one is Shapiro-Wilk test. On the basis of the p-value of both the tests, that is Kolmogorov-Smulders test and Shapiro-Wilk, we can see here the p-value is more than 0.05, more than 0.05, so the data is normal. So you can perform the, I mean, this parametric test. So from QQ plot, we can observe that if all the observations are very close to the line, and if they are making a perfect S, then the data is 100% normally distributed. And but we should go on, we should rely on the tests. If the p-value is greater than 0.05, then the data is normal, otherwise it is not normal. And from box plot, you can see the whiskers are of almost of same length, and the median is there at the midpoint of the I mean box, and you can see here this one is first quartile, this one is third quartile, and this is the second quartile, that is median. So this is 50% of the data, that is Q3 minus Q1, and we know that if the any point is lying at 1.5 times the quartile deviation, then it is known as the outlier, and if it is third time of the this quartile deviation, then it is known as the extreme observation. So here in the data there is no extreme observation, no outliers are there in the data, and you can see from the shape we can see that the data is normal, but we should rely on the test only. Okay, now to perform the independent sample t-test, we go for the analyze, then compare means, and go for the independent sample t-test. You have to put this salary here as it is the test variable, since it is the numerical variable or say continuous variable, and this one is the grouping variable, and you have to define group. Here one is for the say male, and the another one two for female, and then click continue, and if you wish any option, then click that one, otherwise you just click OK. So this one you can see here, this is descriptive statistics, and this is the independent sample t-test. You can see here we have considered 20 male and 20 female. The mean salary for male is 49,900, and it is 39,400 for female, and these are the standard deviation, and these are the standard error for the means. Now we come to the independent sample t-test. First we will see the Levens test. So the p-value for the Levens test is 0.435, which is much more than 0.05. So the data coming from say two independent populations, or the two independent samples are having same variance. So since equal variance assumed is satisfied, so we will consider this one, this line, and we will see this p-value, and since it is I mean less than 0.05, so we reject the null hypothesis, and we conclude that the average salary of male is not equal to the average salary of female, as we can see from the descriptive statistic table that there is almost I mean difference of 10,500 rupees. So it's a huge difference, and it is also verified by the statistical test here. now we come to the pair t-test. So for the pair t-test, first we will see the case study, and then we will perform it on the SPSS through data. So this is the case study of training. ABC University arranged a special faculty development program for one segment of its teachers. The university wants to measure the change in the attitude of its teachers after the FDP, faculty development program. For this purpose, it has used a well-designed questionnaire which contains of 10 questions on the 5-point scale, rating from 1 to 5. 1 as strongly disagree and 5 as strongly agree. The university selected a random sample of 20 teachers. Okay, now we go for the pair t-test. Let me open the SPSS file. Okay, so we'll just go on, click on analyze, then compare means, and go for the pair t-test. So by one you have to put the first one, then after that one, and you go for the option as well. No need of that one, and just click on OK. So you can see here, this is the descriptive statistic for the before and after. So before faculty development program, the mean score is 24.75 of 20%, same 25% score is 33.25 after FDP. And you can see here the correlation between the two, it's a weak correlation. That is why it is not significant. That it means that the two observations are, say, not impacting on each other in the population. So here is the t-test, that is pair t-test, and you can see here the p-value is 0.000. It means it is very significant, highly significant. It means there is impact of FDP on changing the attitude of the teachers, because null hypothesis is rejected, and the null hypothesis is that there is no change in the attitude of teachers after FDP. Now we come to the one-way ANOVA. So let me open the case study. Here we consider the case of store promotion. So an experiment in which a major department store chain wanted to examine the effect of the level of in-store promotion. The experimenter wants to know the impact of in-store promotion on sales. In-store promotion was varied at 3 levels: high promotion, medium promotion, and low promotion. Okay. So you can see here, this is the high promotion code is 1, and for medium it is 2, and for low it is 3. So now you go analyze, then compare means, and go for one-way ANOVA. So here you have to put the dependent variable, that is continuous variable, and in-store promotion factors, and then if you wish to know the polynomial, then put it click here, otherwise you click on continue. And okay, now postdoc test is very crucial and important for while performing the one-way ANOVA. So you can click say on Turkey and say okay. So This is for the equal variance assumed, and say for equal variance not assumed, so we are using the Duncan's test. So click on at 5% level significance, okay, and go for the option. So if you wish the descriptive statistics, a homogeneity of variance test should be there, and then click on OK, and click on OK. You will see that this is the descriptive statistics for high promotion, medium promotion, low promotion. These are the means, these are the of sales, these are the standard deviation, standard error, and these are the 95% confidence interval for the means, and these are minimum and maximum value. Okay, now this is the homogeneity of variance test, that is test for sphericity is there here, and you can see here Levin statistic, and you can see all are non-significant. It means the variance for all the groups, all the stores are same. Now we quickly come to ANOVA, and you can see here that ANOVA is significant. Means p-value is less than 0.05. So the null hypothesis that average sale for all the level of promotion are same is rejected. It means there is impact of in-store promotion. And you can see here, you can have idea from descriptive statistic as well. It is 93, it is 67, it is 40. So they all are different. Are differing. This is differing by 30,000, and it differs by say 25,000, 27,000. So all are having different means. So you can see here all are going to be significant on the basis of the p-value. You can see here every high promotion with medium, high promotion with low, medium promotion with high, medium promotion with low, low promotion with high, low promotion with low, all are going to be significant. And since why this has not been performed here, because you can see here in variance all are not significant. It means the variances for all the three groups, high promotion, medium promotion, and low promotion group, are same. That is why this is not applicable here. So Duncan test is not applied, only Tuckey test is applied, because equal variance is assumed there. So this way you can see for the Tuckey test, these are the per day, the value of alpha is 5%, and you can see here for 1, 2, and 3. These are the correlation type value observation you can see here. These are the mean groups in the homogeneous subsets are displayed. For homogeneous groups, it is the mean for the low, mean for the medium, and mean for the. So you can see here all are given here in descriptive statistics table, and you can compare from this. So this is given for the Tuckey test, and you can see here the performance by same it is 1, and for not same it is not, it is going to be significant with the cross one, this one with this, one with this one with this one with this, and this one with this one is with this. So this way we can see that we can say that the promotion is going to be significant. Now very quickly we will consider the last one, that is repeated measure ANOVA. So here it is the case study. The dietitian introduced new diet chart plan to reduce weight loss. The dietitian took 50 women who considered themselves to be in need of losing weight and put them on this diet for 2 months, rather say 3 months. So their weight were measured in kilograms at the start of the diet, then after 1 month, then after 2 months, and after 3 months. So we will, since all observations are taken on the same group of women, so this is the case of repeated measure. So okay. To perform the repeated measure ANOVA, we will click on analyze, then we will go for the general linear model, and then we will go for the repeated measure. Now you can see here factor name, you can say diet or say weight. And since we are comparing the 4 levels, so you can here say 4 and add them. You can give the major name as well, weight say, and okay, you can define all the select all, and you can define here, and you go for the model. No need to go, we are using full factorial. Continue, then go for the contrast. No need, you can use polynomial and other things. No need, by default it is good one. And you go for the plot as well, so you can plot different charts as well. Otherwise you go for the postdoc test, but there is no need, you have to set the factors here, and so you click on OK. So you can see here these are the I mean, this is linear model, and this is the much least test for the sphericity, and you can see here the p-value is less than 0.05. It means the variances for all the groups are not same. And here we can see within subject, you can see all are going to be significant. It means the diet for every month is going to be significant. It means the diet plan is significant in reducing the loss, weight loss. So this way you can apply the repeated measure ANOVA as well.